Welcome to Center of Math's Advanced Knowledge Problem of the Week. For this week's problem, we're given a linear map P from V to V, where V is some vector space. Also given that P satisfies P squared equals P. And want to prove V is the direct sum of the kernel of kernel of P with the image of P. So to do this, we're going to do two things. We're going to show any vector in V can be represented as the sum of some vector in the kernel of P and some vector in the image of P. And then we're going to show that if we have a vector in both the image of P and the kernel of P, that vector must be 0. And so that will establish that they must be a direct sum. So first, to show that we can represent any vector, it's a sum of a vector in the kernel plus a vector in the image. We're going to write we have some arbitrary vector little v in our vector space. So v equals v minus pv plus pv. These two just cancel. But note that pv is clearly in the image because it's just a vector that we get from applying p to some vector. And if we take p, if we use our linear operator on this left term here, v minus pv, we get p of v minus pv equals pv minus p squared v, which equals pv minus pv. The p squared v by our relation here is just pv. And so this is 0. And so this v minus pv is in fact in the kernel of our linear operator p. And so that's the first part. So now assume little v is both in the image of P and the kernel of P. So that means since it's in the image of P, it's the image of some vector. So v equals pw, w is some vector. But since v is also in the kernel, we have 0 equals pv, since this is due to it being in the kernel. But then since it's in the image, it's equal to p squared w of some vector w, which equals pw by our relation. And pw by our definition is just, by it being in the image, it's just v again, so we have 0 equals v. So v must be the 0 vector. And so we have our vector space v. We can write we can write any vector v in big V as the sum of two vectors, one in kernel P and one in image P. And these two vector spaces have null intersections, so it's in fact the direct sum of the two. And that proves that. Thanks for watching. Please check out centerofmath.org. Check out our blog and follow us on Facebook and Twitter. Thank you.